So today we will dig deeper into the magnetic properties of materials or mediums by discussing the magnetic permeability. What is the magnetic permeability? So as we said, we have to start with the magnetic dipole. And the magnetic dipole, we are considering it as the building block for building the effect of the magnetic field on materials or mediums. Why? Well, we have to recall that any material, right, will be composed of an atomic structure, right? So you have the atomic lattice, you have a crystal of nuclei, and then you have electrons, and then let's draw one atom, right? So we have the nucleus, it's positively charged. You could have a bunch of them, a bunch of protons, for example. And then we have the electron, right? This is the classical picture. And we said that due to the electric field, the electron might, get farther away from the nucleus, or it could get closer to the nucleus. And that effect in bulk along the material, all the millions of atoms, trillions of atoms in the material have this behavior, and that introduces polarization. That is in effect what the polarization is. That's how the electrical dipole moments arise, right? Well, what other thing the electron does around the nucleus? It rotates around the nucleus, right? This rotation around the nucleus is what causes the magnetic dipole moment, which is a very measurable effect, right? A lot of physical experiments are about studying atoms or molecules, and then studying their magnetic moment. It's something that you can very well measure. Okay, but how can we use this inherent magnetic dipole moment that exists all around the material, the medium? How can we use that to examine the property of the material magnetically, and to distill that property into a single constant? That single constant is going to be the permeability. Okay, so how do we arrive there? Right, so we will do that now. Just a reminder, in the case of electrostatics, what we did is that we started with an electrical dipole moment, had units of Coulomb meter, and then we considered a volume in space to have an infinite amount of those dipoles distributed everywhere. Each dipole approaches zero, but when you sum them all up, right, there was a polarization vector. So the polarization vector was just the, I guess let me call this D maybe, right? So when you sum up all the dipole moments, n of them, let's say I from k to n, 0 to n, right? So let's say there are n of them in a unit volume delta V, right? So this gives me, when I do this sum, this gives me the polarization vector. If I take the limit as delta V approaches 0, I get the polarization vector. So the polarization vector is an electrical dipole moment density, so to speak. And it turned out to have the same units as the electrical flux density, right? If I take Coulomb meter divided by meter squared to get the density, I get Coulomb per meter squared, right? And then ultimately we did a calculation where we found that P must be minus divergence rho PV, where rho PV is what we call the bound charge distribution, meaning that we examined the space where polarization is occurring. And we said, depending on the nature of the polarization, sometimes a charge density will appear. And this is not like the free charge density of the free moving charges. This is those are the charges arising from the dipoles that are attached to the fabric of space itself, or to the fabric of the material itself, like the atoms in the lattice of the material, right? And why was this formula useful? This formula was useful because it allows us to go back to the postulate, right, and then add that charge rho PV to the postulate, because the postulate will always be correct. I mean, if there is a charge that arises in the medium due to the polarization, it should still apply to the postulate, right? So this allows us to utilize this, right? And then this becomes rho free charges minus, typically I don't need to write free, right? It's implied, dot P, and then I move that to the other direction. I get epsilon naught E plus P equals rho, right? So here what I've did, I've assumed that polarization exists, calculated what kind of bound charge density does it lead to, depending on this is a mistake. This should be rho PV equals divergence P. Right, so we assumed polarization exists. We discovered that, hey, the divergence of polarization negative gives us, if I give you a certain polarization vector that's distributed over the space, using its divergence, you can determine what's the charge density that appears. This is a charge density that's bound. I don't want to deal with it. So I want to roll it into the postulate, and I get this new field, which is the flux density. And this is how I define my flux density now. So what I did here essentially is I rolled in the properties of the material, rolled in the effect of the electric field on the material into the flux density field, right? So the flux density field includes the polarization due to free space plus the polarization due to the material. Right? That's why D does not depend on the material, because D already includes in it the effect of the material through the P vector, right? While E does not include the effect of the material. That's why E varies depending on what material you're in, because the effects of the material are not included in E a priori, while they are included in D a priori. And then we took a special case, a very common special case. Most materials obey that special case, where P is proportional linearly to E, right, by a term ZE called the susceptibility, and that allowed us to write D in terms of E and have a factor of this parameter between them. This new parameter we called the permittivity, the general permittivity of the material. So the permittivity that includes in it, embeds within it, the polarization that occurs in the material. So this makes things simpler. I don't have to worry about P anymore. I don't have to worry about bound charges anymore. Though P and all the bound charges are already rolled into D, right? And I just have to utilize the simple formula D equals epsilon E. We want to do something that's analogous to this for the case of the magnetic field, and it's exactly analogous to this, right? It's like I mean, we might end up using a curl instead of a divergence, but it is pretty much the same program. Okay. So what we're doing now is we've done in the past. It's nothing new. It's just that now we're doing it with respect to magnetism. Okay, and there are many ways of doing this, and we will stick with one simple way, one simple approach. Okay, so let's go back to the single dipole. So this is my single dipole, right? And we said this dipole has a moment, and let's assume this is the z-axis. The moment of this dipole is going to be I pi d squared n hat, right? Or n I n hat I, and then pi d squared is just the area, surface area of the loop. Okay, so I want to now define, this is the dipole. Now I want to define, I'm going to assume that in my space, there's a bunch of those loops. There's a loop density, meaning any region of space, no matter how small, there's like an infinite amount of those dipoles, right? And each one might have dipole moment of 0, but because there are an infinite amount of them, they converge to some constant value, but there is a density to them, right? How can we define this density? By the way, this magnetic dipole density is what's called magnetization, M. Magnetization. Similar to the case where polarization is just the electric dipole density, magnetization is just the magnetic dipole density in space or in the medium. Right? So how do we define it? M equals, I'm defining it over a certain volume. In a certain volume, I have n dipoles, right? And n could be very large, and delta V could be very small, right? So this is the limit I'm taking here, the limit as delta V goes to 0, right, of the individual moments. What is the unit of this thing? We said the unit of this thing is so this is amp meter squared, right? It's current area. What's current area divided by volume? That gives me amp per meter. Curious that it has the magnetization has the exact same units as the magnetic field intensity. Contrast that with P, which turned out to have the same units as the electrical flux density. So something very similar is happening here. Okay, most materials will have M equals 0, right? Because they have, in the material you have all the dipoles, all the, electrons are spinning around the nucleus. That's fine, but they're all spinning in different directions. So this is the M, right? So the direction of spinning is all different, so that effectively it cancels out, and we end up with M capital equals 0. Okay, so because the dipoles are randomly oriented. Okay, so M is a dipole, magnetic dipole density, and it's called magnetization. Well, what is then, for a small region of space, small volume of space, what is the dynamic, what is the magnetic dipole moment then? Again, I mean, you take a density, you multiply it by volume, you get the thing, right? So for a volume dV prime, and it's a differential element, right? The differential magnetic dipole density is going to be M dV prime. Okay, so this is the dipole moment of an element volume. Dipole moment of dV prime. Okay, what is dA? What is the magnetic vector potential due to this infinitesimal dipole moment? Well, we derived that formula in the last lecture. This should be nu naught dm cross r hat over 4 pi r squared. So let's say we want to find dA at this point, right? This is going to be r hat is going to be in this direction, right? And then dm will be whatever the orientation of the dipole within that small volume space. So this is a correct formula we can integrate it. Well, before we integrate it, let me plug in, instead of dm arrow, let me plug in m, right? So I end up with this formula: dA equals nu naught m cross r. You know, I want to relate everything as a function of m. For pi, instead of r hat, I want to do r. But how do I get back r hat? Just divide r vector by r, right? Magnitude. So I end up with r cubed dv prime, right? And then the complete magnetic vector potential is just going to be mu naught over 4 pi, the volume integral over all of space, or over all the whole medium or the material, m cross r over r cubed dv prime Weber per meter. Okay. How do we get B? We get B by taking the curl of A. Right, and this is a correct formula, although I mean it's not very useful. I mean we rarely have to use that formula to calculate the magnetization, right, or to calculate the effect of the magnetization, but this is a good starting point. We derived a similar formula for P before we moved on and tried to describe P in simpler terms. For P, the way we simplified it is we tried to deduce what is the volume charge density and the surface charge density on the boundary of the medium associated with P. For M, to simplify things, what do we need to do? So for P, we looked at volume charge density, bound charge densities, and surface charge densities associated with P. Any orientation of P, any random P in space is going to be associated with certain rho PV and rho PS on the boundary of the medium, right? And we simplified by doing this calculation. For M, you know, electric flux density fields typically arise from charge distributions, right? What do we said M has the same units as the electric field, magnetic field intensity. So what do we expect M to give rise to? We should expect M to give rise to magnetic, bound magnetic, bound current, bound magnetization current distributions, right? Volume current distribution, let's call it GM, and surface currents on the boundary of the surface. So in the same way that P is tied with the charge distributions, M is tied with charge densities, and we're going to show you, I'm going to show you how. It's really very simple to derive it, or to conceive of. It's not that difficult. You can think of it that way, right? If you have a bunch of loops distributed in space, what happens if all the loops are the same, if M is uniform? So I have this loop, and then I have this loop next to it, and then I have this loop all in the same direction. M is uniform. The currents are the same in each of those loops. So at each boundary, let's say I have a boundary between two loops, I have the current going here clockwise from this loop, loop 1, and then from loop 2 the current is going, the same loop, right, is going counterclockwise. Right here the current is going clockwise, here the current is coming in counterclockwise, so the currents cancel. So effectively, if there's a uniform magnetization field, all the loops cancel each other and there is no effective magnetization current that is going to exist in the material, right? So if M is not uniform, is varying, there is going to be some kind of current that arises in the material, and that current is going to be the way we tie M to the magnetic field by taking that magnetization current and tying it to Ampere's law so that we can tie magnetization to the magnetic field intensity and embed the properties of the magnetic material through permeability into the H field. Okay, so that's where we are getting. So how can we do this? Well, let's assume M is not uniform in a certain region of space. Right? Let us zoom in. Let's zoom in a small region, very small region, where M is uniform. M is uniform within this region, or the loops are uniform. Right? And let's assume this small region is kind of cylindrical. We can assume anything we want, right? So this is a very small region that kind of looks cylindrical. We can make it look like anything we want. It's a matter of choice, right? So what happens to all the loops, the dipole loops inside? So let me draw the cylinder bigger. Although I'm drawing it big, this is a very small volume, right? Why do I want to go to a very small volume? Because I want to get to a region of space where M is uniform. So what happens here, I have a bunch of loops. Those adjacent loops next to each other cancel each other out until I get, like if I have one loop and then another loop like this, and then I add them up, and on their intersection, the loops are going to cancel, and I'm going to end up with something like this. Right? So what will happen is all the loops are going to cancel until I end up with a loop that looks like a bunch of spirals, like a bunch of loops that are looping across the whole cylinder like this. This, right, and there's an infinite amount of them. We can imagine this to be a sort of a spiral, right? Where at any point we can cut the loop and join it to the loop right next to it, above it. Well, that won't change a thing. So we will get something akin to a spiral. We will get something akin to a solenoid, right? And we know how to calculate the H field of the solenoid, right? So we can use this fact that all the dipoles, if we kind of like cut them up and join them as a solenoid traversing across the axis of this very small cylinder, this will look like a solenoid. And we already know what the magnetization. So there is a certain field intensity due to the magnetization that we can calculate, and we already know how to calculate that. That's just N I, right? N is the number of dipoles per unit length, right? Let's assume that this is the z direction, by the way. So this is going to be z hat. This is a vector, right? Let me write this as N over L I z hat. No, okay, so now I want to do one small change. I'm going to just multiply. What do I want to do? I want to multiply the numerator and the denominator by pi d squared. D is the diameter of those loops. This is D. Nothing changes, right? I just multiplied by pi d squared. What do I end up getting? What's pi d squared I? Pi d squared I is just the magnetization, the dipole moment, right? It's not the magnetization, it's the dipole moment. And then I have N over, what's pi d squared? Pi d squared is the surface area of one of those loops, and L is the length of this very small element. So what's pi d squared? The surface of the cap of the cylinder times the length of the cylinder. That's the volume of this very small element. Right? So, but what is this? What is the magnetization per loop? This is the dipole m. Small m is the dipole moment per loop. So what is the dipole moment per loop multiplied by the number of dipole moments divided by the volume? That's the dipole moment density, right? So we are summing up all the dipole moments, we're dividing them by the volume. That's exactly what the dipole moment density is. So this is M, right? So this tells me that M is really, so we verified it logically now. Previously, we noticed that the units of M are the same as the units of the magnetic field intensity. Now we have verified it conceptually that M is actually the magnetic field intensity due to magnetization. Okay, since M is an H field, right? Ampere's law applies, right? This H field should have a curl, right? I mean, it's an H field, so Ampere's law applies to it. So what's the curl of an H field? The curl of an H field, according to the postulate of magnetostatics, has to be some kind of current, has to be a current density. This is the current density due to magnetization. Okay, what about the surface current density? Well, I mean, if I take any surface, let's look at the loops. Oh, by the way, this has ampere per meter squared, right? J has units of ampere per meter squared. Well, I mean, the surface current density is easy, right? So take a boundary, right? On this boundary, if the magnetization is pointing out, that means that the loop is on the boundary, right? The loop is not, the current is not going out of the boundary. So there is no, right? So all the small loops are on the boundary. So if I zero in on this boundary, I see all the loops like this, and all the loops cancel each other, right? What if M is tangent to the boundary? Like M is like this, let's say. It's, let me draw it as some X, meaning M is pointing in there. So if I zoom at the boundary, observe the boundary from above, I will see I'm looking at the loops edge on. So I'm seeing the loops like this on the boundary. Because I'm looking at the loops edge on, the currents in the loops will not cancel each other. I'll end up with a certain surface current density, right? I mean, it's easy now to see when does a surface current density arises. It arises when M is 90 degrees with respect to the surface normal vector, right? Only then does a surface current density arise, and we can write it as such, right? It's M cross N hat. Very similar to the case with polarization. So this is what we got. So think about this. This is very easy to deduce. Right? So we end up with those two expressions. The curl of M equals the magnetization volume, volume magnetization current density has units of amp per meter squared, and then the surface, the current density, the surface current density on the boundary of the medium is just going to be, if I have a medium, I have N hat, it's going to just be M cross N hat, and it's going to have its current that's flowing on a surface. So because if I have any surface and I have current flowing on the surface, it's going to be current distributed it's like the surface is like a sheet. So it's a current flowing in a sheet, right? What's the current flow density for a current flowing in a sheet? It has units of amp per meter, right? Every meter of the edge of the sheet has a certain amount of current flowing through it. So the units here are amp per meter. Okay, those are the relations that relate magnetization to magnetization currents. Okay, in the same manner as we did in electrostatics, the bound magnetic currents, magnetization currents, are not the end of this argument, right? We only need them because we want to tie magnetization to the H field through Ampere's law. In the same way we wanted to tie polarization to the D field using Gauss's law. Right? This is the sole purpose of this. Now we found Jm. Okay. Now since I found Jm, I can go back to Ampere's law. Right? This is Ampere's law. Right? And now I know that if there is magnetization in the material or in the medium, J, the electrical free current, this is the free electrical current, is not the only current that exists. There is a magnetization current too. But I don't want to deal with this current. I want to somehow embed it into H so that I don't have to think about it anymore. Right? So the way to do that is to first, I want to have a new H. In the same way I have a new D now that incorporates both the polarization due to free space and the polarization due to the material or the medium. In the same way, I don't want to use this H now. I want to embed. So I want to embed H on its own. I can look at it as a magnetization of free space. I can look at it that way. It's valid to look at it that way. But I don't want to use this now. I want to embed Jm into a new H. So instead of H, I'm going to put B over mu naught, right? That's valid for free space. The relationship between H and B fields is mu naught, right? This is the relationship in vacuum between the magnetic flux density and the electric field intensity. I want to put in B instead because I don't want to have the old H. I want to define a new H that incorporates, that has embedded in it the properties of the material, right? In the same way that I defined a new D that has embedded in it the properties of the material. Okay. This is still Ampere's law, right? Now I go to work. Right, mu naught minus Jm, just rearranging, equals J. Remember, ultimately, I want to forget about Jm. I want to embed it in the field. So this is going to be B over mu naught. Instead of Jm, this is curl M, right? Equals J. Okay, and we know that the curl is linear, so I can do this minus M. Okay, so this is now my new H field. This is the H field that incorporates, embeds magnetization within it. Right? And if I use that, I get the original Ampere's law, only now with respect to only free currents. I don't have to worry about the bound currents anymore. They don't exist as far as I'm concerned anymore, insofar as I can imagine that they exist, but when I do the mathematics, I only deal, when I solve problems, I only deal with the free current. And this H is going to equal B over mu naught minus M. In the same way with that D turned out to be epsilon naught E plus P. Very analogous situation. Okay, and we could stop here. We've successfully incorporated the effect of magnetization into the H field. But we could go further. We could recognize that for many materials, I can describe the effect, I can describe the relationship between M and H, the total H, to be proportional. I can say that M is proportional to the total field H intensity. So it's going to be some constant multiplied by H. So if I have a certain H, I should expect M to be some constant times H. I could write M as follows. And this is called the magnetic susceptibility. Right? And this allows us to derive an even more useful constant. So let me plug this in. So H equals B over mu naught. Instead of M, I put in susceptibility MH. I can take this to the other side. Oh, before I take this, yeah, I can take this to the other side. I end up with 1 plus susceptibility M H equals B over mu naught. And then I get H equals B over mu naught 1 plus. And typically people write it like this. U naught 1 plus Zm H. This is called the relative permeability, and then mu naught mu R H is the general permeability for the material. This will vary depending on the material, depending on how well the material magnetizes. So we end up with this formula, right? Similar to the electrostatic case where we ended up with D. So this is a lumped representation. This is a lumped incorporation of the effect of magnetization. Okay, right? The main difference between the electrostatic case and the magnetostatic case, and this main difference, by the way, arises solely because we represented the effect of the medium in electrostatic case by dipoles, charges that are a certain distance between them, while in the case of magnetostatic, we represented the effect of the material magnetization by loops of current, right? So this causes the difference. If this makes it such that D is the composite field in electrostatics. D includes the polarization of free space, of vacuum, plus material, right? While E is just an external field, does not depend on, I mean, E does not include information about the material. D has information about the material embedded in it. That's why D does not vary when we solve problems, while E will vary depending on where you are, which part of what kind of medium you are in, because E does not have in it information about the medium, while D comes with information about the medium baked into it by the constant epsilon. In the same way now, H in the case of magnetostatics, H is the magnetization of vacuum plus material. H has the information about the material baked into it, right? And the only reason it's the field intensity in this case, not the flux density, is because we are representing the dipole as a loop. It's a mathematical result, right? If we were representing the dipole as two magnetic charges with the distance between them, B will become that field that carries the information about the medium, right? And that's why in magnetostatics, in contrast to electrostatics, because H already has information about the medium in it, baked into it, H does not vary between mediums when we solve problems. It's B that's different, right? H does not depend on the material. If you look from Ampere's law, H only depends on the J, right? So similar to Gauss's law, where D just depends on rho. And then after we find D, it's E that will have different values depending on the material. Same way here, H will have the same value regardless of the material because it already has the information about the material embedded in it. And then B will vary between mediums depending on the different constants. I hope you get that point, right? Otherwise, that's the two situations mirror each other quite well. Okay, and that's the gist of it. So now we can use this constant, the permeability, to classify different kinds of magnetic materials. The major types of magnetic materials that you'll encounter are what's called diamagnetic materials, paramagnetic magnetic materials, and then ferromagnetic materials. Okay, so off the bat, you notice that in contrast with electrostatics, magnetic phenomena can be a bit more varied and more subtle and detailed, and in many ways harder to model than dielectrics, for example. Although there are some hairy dielectric materials, right? But off the bat, magnetism seems to be a little bit more difficult to model, and in fact, many models of materials are not exact. They are more like empirical models. It's a very huge field of research, essentially modeling magnetic materials and understanding theoretically how do the properties of magnetic materials arise. The permeability is just the beginning. Okay, so what's the major distinction between those three kind of materials? Well, the major distinction is the relative permeability. So for diamagnetic materials, the relative permeability is less than 1, slightly. So it's not 0, it's just slightly less than 1. So if mu r, let's say, is around 0.999, let's say, or 0.98 or something like that. So whenever you see relative permeability that's slightly less than 1, that tells you that this is a diamagnetic material. This tells you, right, mu r is 1 plus susceptibility, right? So that tells you right away that the susceptibility is small and negative. Okay, this is peculiar. What does that mean? That means for this material, if I apply an H field, let's say from some J current, and I have an H field and it acts on that material, the magnetization that happens in the material, right? So this is negative. So you know that the magnetization is going to be susceptibility times the magnetization is going to be susceptibility times H, right? So that tells me that the magnetization is going to oppose this acting field, right? So this is a peculiar thing for it to happen because if we're used with dielectrics, we're used to the fact that the dipole stretches with the field, right? While here in this case, the magnetization opposes the field. Why does this happen? I mean, to understand exactly why that happens, you have to understand the model of the atom. So the atom is a nucleus, and then you have a bunch of electrons spinning around, right? And this is, I mean, this is not exactly a classical model. This is a quantum mechanics model. So there are dipole moments, there are magnetic moments due to two components, due to the orbit of the electrons and due to the spin of the electrons, right? And typically for most materials, and most materials are diamagnetic materials, those atoms are not magnets per se by themselves, meaning that the orbital magnet moment exactly cancels out the magnet moment due to the spin of the electrons. Now, spin could be understood, if you want, classically as an electron spinning, but first and foremost, it's a weird quantum mechanical property of the electron. It's not literally spinning, but it is behaving as if it's spinning in a similar way where the electron is behaving as if it's a particle and as if it's a wave, right? But we won't get into that. The gist of it is that this interaction between the spin and the orbit of the electron behaves in such a way such that the effect, and this is a quantum mechanical effect, you cannot explain it, it's hard to explain classically. The effect of an external field is to make the moment of the orbit versus the spin unbalanced, meaning one will be slightly larger than the other. And this imbalance is going to show in a way such that the magnetization field is going to oppose, right, the external magnetic field. Right? So most materials naturally will be diamagnetic. They will oppose the magnetic field a little bit, right? So if I have like a magnet, north, south, and this is a diamagnetic material, effectively the material is going to generate a field that's opposite to the field coming from the magnet, meaning it will be like north here, south here. So it will be repulsed. This effect is, by the way, very weak. So it's hard to measure, but it's there for most materials. Right? This effect is so weak that for many materials it gets swamped by bigger effects. Those bigger effects are the effects that we talked about. We care about when we study materials that can be considered magnetic. Diamagnetic materials can be considered non-magnetic materials. They poorly or weakly interact with the magnetic field, right? But for the purpose of this course, all you need to know about diamagnetic materials is that their permeability is slightly less than 1, with one exception: superconductors. So if I have a loop of a superconductor, the relative permeability is 0, meaning the susceptibility is -1 completely. What does that mean? That means that if I have an H field, I don't have a B field, right? Mu R mu O, that equals B. If mu R is 0, that means there is no flux density field to the H field. So if I have an H field, there is no B field inside the material. This is one of the things that make the superconducting materials completely lossless conductors. Because if there was a B field inside, it will interact with the moving charge and it will take away energy from the moving charge. But because there is no B field inside, right, there won't be that energy exchange. So yeah, superconductors are the one exception where mu r is 0. It is a diamagnetic material, but most diamagnetic materials have mu r closer to 1, slightly less than 1. Now, paramagnetic materials are more common and they have a mu r slightly larger than 1, right? So those are materials where this quantum mechanical effect of the interaction between the orbit of the electron and its spin exists, but is so weak and is so overpowered by a bigger effect where the atom itself acts as a magnet. The atom itself has some net moment. So it doesn't have a moment in diamagnetic materials. The slight moment that opposes the field arises due to the effect of the field, right? In paramagnetic materials, the material itself, the atom itself is magnetic, but the thing is, all those magnets, all those moments are randomly oriented. So, and they are pointing everywhere, so they cancel each other out, right? And when you apply an external field, all you're doing is orienting the field with the external field, and that orientation increases the flux density inside the material. So for those kind of materials, mu r is slightly larger than 1. right? It might be 1.001 or 1.01, right? A lot of materials are paramagnetic. Air, for example, is paramagnetic. I believe some, what else is paramagnetic? Some metals are paramagnetic, right? Okay, so this is the second kind of material. By far the most interesting kind of magnetic material, and the material that shows a lot of complexity that does not exist in dielectrics, is the ferromagnetic material. I mean, there's tons of research and work still to this day on trying to understand fundamentally ferromagnetism. Ferromagnetism is its own huge field, and we cannot even cover 0.01%, 0.001% of it in this course. I mean, it's one of those things that requires its own introductory course and even a bit more supplementary higher level courses, right? But the basic thing you need to know when you think ferromagnetic materials is that mu r is much larger than 1. Mu r could be in the hundreds or the thousands or the tens of thousands, right? And then mu r is nonlinear, right? The material has nonlinear, and then the material has memory, right? So that's the big thing. So remember, in dielectrics, we said epsilon, if we plotted E versus D, right? We said the material, epsilon is mostly linear, it's the same. And then we reach a point where the material just breaks down. You know, the atoms keep polarizing until the field gets so large that the atoms break apart, and we get plasma or whatever. The thing burns, right? Ferromagnetism is a bit more complicated in the sense that mu itself is a function of H in the case of ferromagnetism. That's one. So there's this nonlinearity. Of course, mu is large, right? And then there's also this memory effect, meaning the material can remember that it's magnetized. So that's why you can take stainless steel, like a screwdriver, magnetize it, and then remove the magnet. The material will remember that it's magnetized. This effect, I mean, again, we cannot do it justice, but suffice to say, the very high level explanation is that this material tends to be separated into domains, and each domain will have like a bunch of atoms, like it'll have, like, let's say, millions of atoms. Those domains are peculiar in a way where the electrons on those atoms share the same spin. Remember this quantum mechanical property that's kind of like spinning, right? So in this domain we might be spinning this way, in this domain we might be spinning around this axis, right? So what happens is, when we apply an external field, those spins tend to align with the field, but then those spins tend to have some sort of elasticity where if they align to the field, but then they latch to each other. They latch to each other, and they support each other, so that even if we remove the field, they are kind of like chains attached to each other that stop each other from getting disorganized again. The way to get them disorganized is to apply heat them up. Let's say if I heat them up, apply energy, make them vibrate more, they will get disorganized again into separate domain, right? But then if I apply a little bit of energy, they kind of like snap into place, right? And that effect is what gives us memory. It's kind of like if you're like on a hill and you have a slump here, and then you have a long valley, right? And then you're here, right? But then, so this position is the disorganized position. And then you apply a little bit of energy. This energy is the external field, right? This energy is enough for you to roll down the hill and get into a more organized orientation, right? You need energy to get into the disorganized state. So this is the gist of ferromagnetism, and one big way to see this effect of memory and nonlinearity as engineers is to look at the lumped BH curve. So we said here, instead of the relationship being linear, right, the relationship will look something like this. We start at 0 when mu is 0, when h is 0, b is 0. This is the magnitude, right? And then we would go up, right? So we have some initial mu, which is the slope between b and h, but then we start to taper down until we hit, maximum h, and here we hit mu minimum or mu saturation. We reach a point where even as much, doesn't matter how much we increase the h, we stop getting more flux density, right? This is called the saturation point. Ferromagnetic materials saturate, right? And then the effect of memory can be seen. Let's say we run the experiment, we increase h until we hit saturation, and then we reduce h. When we reduce h, we don't go back along the same curve. The effect of memory manifests itself by the curve looking like this, something like this. So by the time we hit back to h equals 0, there is some latent magnetization that remains in the material. This is like the screwdriver that retains some magnetization. In fact, to bring the magnetization back to 0, we have to apply the field in the opposite direction. H has to go negative, right, until the field goes back to 0. And then we go down, and then if we continuously go back up and forth, back and forth, back and forth, and back and forth, we get something that's called the hysteresis curve. BH hysteresis curve. And this encodes the nonlinearity of mu and encodes the memory effect of ferromagnetic materials. If we plot mu versus h, no, well, mu, we're plotting mu versus the path, right? So we start at mu initial, and then we go to some mu maximum, and then when we hit saturation, we go to some mu minimum. At close to saturation, mu gets very close to 0. Ferromagnetic material acts like a superconductor. Well, it's not a superconductor, but it has that behavior when mu becomes very small. And by the way, this hysteresis curve is going to depend on the frequency of frequency of h, how fast we are varying h. If we vary h slowly, we might get a thin curve like this. If we vary h very right at a higher frequency, you might get something like this. So it's dependent on how, it's also dependent on how fast we vary h. So it's a pretty complex phenomena, but the HB curve is a good way to visualize it. And if you do a lot of magnetics design, you will encounter this curve a lot. All right, so yeah, so we'll continue next time. But that's as far as those are the 3 kinds of different magnetic materials you should be aware of, and you should at least qualitatively understand the differences between them. In magnetic design, you will mostly be concerned with ferromagnetic materials. If you design a transformer or you design an inductor, you would be utilizing ferromagnetic materials. So you should expect to see this BH curve a lot in your studies. All right, thank you guys.